All right, so our presentation is about flexible joints. This presentation is about its cradle-to-cradle certification. The idea for flexible joints actually came to me from nature, or came to us from nature. Nature doesn't use a lot of part counts and doesn't just use different parts to achieve one function. It uses the same part with different properties to achieve the same function. And this is where like I started looking through actual practical applications and in specifically a door. So a door would have two hinges, a frame, and the actual solid door with the doorknob. That's way too many parts, and a lot of these parts are not recyclable. A lot of these parts would just end up in a landfill at the end of their lifetime. So what we focused on is we focused on the idea of replacing the door and the frame with a mechanism that would let it open and close without any moving parts. So that would be flexibility mostly. We had to rely on it being easy and cheap and accessible, so we went to 3D printing. 3D printing would use a print head that would overlay essentially what the door would look like, and we could use extrusion and slicing to produce multiple units at once. That would make the door significantly cheaper, and it would also just reduce the amount of waste needed uh, in the design process and in the manufacturing process.
Okay, so for making our product cradle to cradle certified, as compared to other regular plastics that might take like 450 years or longer to biodegrade, we're planning on using the ultrafuse TPE 60D, which is a flexible and biodegradable polymer, as a replacement for just regular non-biodegradable plastics. So the way this should work is that even when the product is no longer being utilized or it's being discarded, it should this specific plastic will be able to biodegrade and thus be have its resources returned back into the ecosystem.
On the topic of material health, a 3D printed door will be a lot sturdier than your standard wood one. And since it's made of plastic instead of wood, it won't be susceptible to forces like rot or termite. And as for material reutilization, this is a bit of a toss-up. Standard 3D filament would take a long time to biodegrade. However, it could be melted down and reused for future prints. But biodegradable filament would help reduce plastic waste.
In terms of the energy used for our 3D printers, per printer, each one uses 8 kilowatt hours per day, 12 hours daily, so 96 kilowatt hours per day, and 3,000 kilowatts per month. So if we wanted to go full renewable on our production side, it would require 84 300 watt panels to replace 100% of our energy. It's the equivalent of 1,500 square feet, so a small house. If the warehouse itself isn't very big, we won't be able to put them on the roof. We may have to have land around the production facility to take care of that. Now in 3D printing, we don't need to use any water, as any stray filaments will just be air sprayed off at the end.
In terms of positive effects for the community, there would be lower use of materials such as wood, and this would contribute to having a better air quality because you'd have less trees going into homes. And then it's made with one material, so it's extremely easy to be remanufactured or biodegraded. And this would contribute to a fair and equitable society as it would reduce pollution because we could use more of the same material to make one thing. And according to Minnesota Pollution Control Agency, poorer communities are the most affected by pollution. So in reducing pollution, we will contribute to a more fair and equitable society. So this was our presentation, and thank you for watching.